My name is Milad Soltanalipour. I'm a doctoral student at the Polytechnic University of Catalonia. I will be presenting a study on an innovative shear transfer system for concrete-filled steel tube in columns. This presentation is organized into the following sections. After the introduction, we will have a look at the current shear transfer systems. We explain their limitations and how these limitations can be overcome with the new shear transfer system presented in this study. Then the experimental test will be described and the most important conclusions will be mentioned. Concrete-filled steel tube CFST columns are frequently used in construction due to their high ductility and improved load-bearing capacities. The steel tube restrains the lateral expansion of the concrete core, and the concrete core prevents the inward buckling of the steel tube. Therefore, CFST columns can provide a good composite action between the two materials. In the beam to CFST column joints, gusset plates are used for transferring the loads from the beam to the column. The gusset plates are executed either by cutting the steel tube or by welding the plates to the outer steel tube. In the first case, the shear transfer between the beam and column is guaranteed by the friction between the gusset plate and the concrete core. In the second, the shear transfer should be provided by shear transfer elements, such as shear studs, internal rings, angles, steel plates, steel bars, tab stiffeners, etc. The current shear transfer systems enhance the shear bond resistance, but they may slow down the construction process due to their complexities of execution. In addition, due to the flow restrictions, pump filling the tube is more difficult than the case of conventional flat columns. This research proposes a new system that is easier to be massively produced. It simplifies the beam to CFST column connection and provides no flow restriction when casting concrete. For these reasons, it provides competitive and economic advantages by reducing the energy, time, and costs of a construction project. In this presentation, we will evaluate the shear bond resistance, failure mode, and energy dissipation capacity of the new system. We also show the construction process and some videos of the test to have a better insight into the UPC CFST columns. The UPC patent includes a series of small crown-shaped breakages created on the steel tube through punching. The crown-shaped punches embed inside the fresh concrete, and after it hardens, they resist shear forces. The set breakages, which are distributed along the whole length of the column, enhance the shear transfer capacity between the concrete core and the steel tube. As it can be seen, no welding is required to connect the shear transfer elements, as they are created by punching the tube only. It can be added that the existence of punches brings fire protection by preventing spalling phenomena, which will be addressed in further investigations. For evaluating the system, a prototype has been tested. The performance is compared with another specimen with identical dimensions and mechanical properties, but with a flat conventional interface. The construction of the steel tubes begins with punching. The steel plates are folded into the L profiles, and the two profiles are welded from the exterior surface to build the hollow square section. No attempt is made to change the roughness of the tube interior surface in none of the specimens. The UPC steel tubes should be covered to prevent dripping during the concrete casting. To hold a place for the air gap in the free end, an expanded polystyrene block with 40 mm depth is placed at the bottom of the tubes before casting the concrete, and it is taken off before the test. The push-out test setup can be seen in this slide. A hydraulic jack with 400 kN capacity applies the force on a 40 mm thick steel block placed on the concrete core surface, which is used to distribute the force. In the push-out test setup, the force is only applied to the concrete core to push it out from the tube. Given that, along the 50 mm length at the loaded end, the steel tube is kept flat, and it has no punch. This is to avoid the contact of the load spreader block with the punch crowns. It should be noted that since the concrete finished surface is not polished, a thin layer of melted sulfur is applied. It provides a flat surface that will be in contact with the steel block. The slip is measured using two transducers with a 50 mm displacement capacity, pointing the load spreader block. The axial deformation of the tube was also recorded. This allows excluding the vertical deformation of the steel tube from the slip measurements. This figure shows the bond slip curves. The shear bond resistance is enhanced using the UPC CFST technology. It provided the shear bond resistance of 0.99 megapascals, which is 2.44 times greater than the flat interface. The shear bond strength is determined as the applied force per unit area of the steel-concrete interface. The curve begins with a linear stage and it is followed by a nonlinear ascending part until the maximum resistance and has a softening part. But in the flat interface, after the initial linear stage, the resistance drops in a brittle manner. The absorbed slip energy is a good indication of the bond slip behavior of CFST specimens after the initial stiffness. It is defined as the area underneath the force slip curve in the zone between the initial stiffness and where the force drops to 85% of its value. In the UPC CFST specimens, the absorbed slip energy is 4.24 kJ, but in the CFST specimen, the slip energy is 0 due to its brittle failure. After testing, the steel tube was cut to describe the interactions. The failure mode in the prototype is the crushing of the concrete in front of the punches. In the side bands near to the corners of the tube, the crushing is more significant, which shows that they are more efficient in transferring shear forces. The failure mode of the conventional CFST is a slip with no significant change on the concrete core appearance, except the frictional marks in the corners of the steel tube. Further research has been carried out after this paper was prepared. Based on the observation made on the concrete core, the design has been optimized. In the UPC CFST prototype, a net of punches with equal horizontal and vertical distances of 40 mm exists on the four sides of the steel tube. But in the optimized design, the steel tube consists of punch bands only at the side near to the corners, because they are more efficient than the central bands. Moreover, the distance of the punch bands to the edge of the tube is reduced to 25 mm, which was 36 mm in the prototype. This change is to take more advantage of the higher rigidity provided in the corners of the section and increase the interaction of punches with the concrete core. As the bond slip curve shows, the final design is more efficient than the prototype due to optimized punch configuration, providing 1.6 megapascals shear bond resistance with 57% enhancement. Reducing the horizontal distance of the punch band to the tube edge has provided a deeper and more significant crushing. The prototype and the optimized design punch arrangement have a 40 mm space between punches. To find the optimum punch density, an experimental campaign has been developed, and the vertical spaces between punches 20, 40, 60, and 80 mm have been studied. The prototype and the optimized punch arrangement are in the group of high-density specimens. The ultra-high, medium, and low densities correspond to 20, 60, and 80 mm space between punches. Smaller cross-sections and higher-strength concrete have also been studied, and in total 56 tests has been carried out in this research project. In general, the HT arrangement is the optimum punch density in both cross-sections. If the density is too high, the interference between punches reduces the shear bond resistance. In this case, the bond slip curve becomes brittle, and as it can be seen, ultra-high density specimens include a sharp transition from the initial line to the descending branch. The failure mode in all UPC CFST specimens is concrete crushing in the front of the punches, as can be observed in this video. The local buckling appeared only in the specimens with the small cross-section and in the space between punches. In this presentation, the shear bond resistance, failure mode, and energy dissipation capacities of the UPC CFST prototype have been evaluated, and other experimental results have been briefly mentioned. This system is easy to be massively produced, simplifies the beam to CFST column connection, and provides no flow restriction when casting concrete. The research project has been funded by the European Regional Development Funds through the Agency for Management of University and Research Grants, Government of Catalonia. Thank you very much for your attention.